Imagine standing on the bank of the Susquehanna River in 1830. The water is wide, the current is cold, and on the other side, maybe 150 feet away, there is a wagon loaded with grain, a farmer with his hat in his hands, and a problem that has existed since the beginning of American civilization. How do you get across? You wait for a ferryman, you pray the water is low, you watch your wheels sink into the mud and you pull the oxen harder. Sometimes you make it, sometimes you lose the wagon, sometimes you lose more than that. This was the fundamental geographic reality of early America, a continent laced with rivers, cut by ravines, interrupted by gorges, and every single one of those obstacles was a tax on time, a tax on goods, a tax on ambition. Before the railroad came, the American economy moved at the speed of a horse. At best, a heavily loaded freight wagon could cover 15 miles in a good day over a decent road. In bad weather, over soft ground, through river mud, that number dropped to 5, maybe 3. The Erie Canal, finished in 1825, was considered a revolutionary breakthrough because it allowed goods to move from Buffalo to New York City in about 10 days. 10 days for 363 miles. That was the miracle of the age. And even then, you were still at the mercy of the seasons. Ice shut the canal for months every winter. The railroad changed everything, except for one thing. The railroad still had to cross the rivers, and the men who built America's first railroads were not bridge engineers. They were surveyors, mechanics, former canal diggers, self-taught mathematicians working with slide rules and guesswork. They had no textbooks. There was no engineering school in America that taught bridge design, because bridge design on this scale had never been done in America before. What they had was wood. Wood was everywhere. America in 1830 was a forested continent. White pine, white oak, hemlock, chestnut, timber of a quality and abundance that the world had never seen. You could fell 100-foot white pine in the morning, mill it by afternoon, and have it on site by the next day. And so the men who built America's first railroad bridges did what Americans always did when confronted with an impossible problem. They built something anyway, and they made it out of wood. The story of the wooden railroad bridge is really the story of 3 men and one elegant, brutal problem. The problem was this. How do you take a structure made of a material that rots, burns, and cracks, and ask it to hold, repeatedly, reliably, something that weighs 200 tons? A loaded freight locomotive by the 1870s weighed between 120 and 180 tons. Add the cars behind it, add the dynamic impact of steel wheels hammering over wooden ties at speed, add the vibration, the temperature changes, the rain soaking into the wood grain, and the question becomes not just engineering, it becomes philosophy, it becomes an act of faith. The first man who answered that question seriously was Theodore Burr. Burr was a Connecticut native, a millwright by trade, and in 1804 he patented what would become known as the Burr arch truss. His insight was deceptively simple. Combine a long, shallow arch, which distributes load laterally, with a multiple king-post truss, which distributes load vertically. Neither element alone was sufficient. Together they created a structure that was redundant in the engineering sense. If one element was stressed beyond its limit, the other absorbed the excess. The Burr arch truss was first used on covered highway bridges, but its principles would migrate, eventually, to the railroad. The second man was Ithiel Town. Town was an architect from New Haven, and in 1820 he patented a design so simple it looked almost too simple. He called it the lattice truss. Instead of heavy timbers in a complex arrangement, Town proposed using hundreds of thin, overlapping diagonal planks, typically 2 inches thick by 9 inches wide, fastened at every intersection with wooden pins called treenails. The beauty of the Town lattice was twofold. First, it could be built by ordinary carpenters with ordinary tools. You didn't need a master framer, you needed a pile of 2-inch planks and a man who could drive a wooden pin straight. Second, the structure was redundant to an extreme degree. Damage any one or two diagonals, and the load simply redistributed through the hundreds of others. The bridge kept standing. Town was shrewd enough to patent the design aggressively. He charged $1 per foot of bridge built using his method, and $2 per foot if he found out you had copied it without paying. He made himself a wealthy man, but the man who matters most to the railroad age is William Howe. Howe was a Massachusetts millwright, and in 1840 he patented the Howe truss. On the surface it looked similar to existing wooden truss designs, diagonal wooden members in compression with vertical members in tension. The revolutionary change was this. Howe replaced the vertical wooden tension members with iron rods and turnbuckles. This was the breakthrough. Wooden vertical members in tension were the weakest point in any timber truss. Wood under tension splits along the grain, but iron under tension is extraordinarily strong. By replacing just those vertical members with iron, Howe created a hybrid structure, still primarily wood, still buildable by carpenters, still cheap but dramatically stronger and more reliable than anything that had come before. The Howe truss became the standard railroad bridge of the 19th century. Thousands of them were built across America. They carried trains from Massachusetts to Missouri, from New York to Georgia, and they held, at least most of the time. To understand how a wooden railroad bridge held 200 tons, you have to stop thinking about wood the way you think about wood in a house. In a house, wood is holding things up. A floor joist is a beam in bending, weight pushing down in the middle, ends supported. This is actually one of the weakest ways to use wood. Bend a plank far enough and it breaks at the bottom face where the fibers are in tension. In a properly designed truss bridge, almost no member is in bending. Instead, every member is either in pure compression, being squeezed, or pure tension, being pulled. And wood is remarkably good at both. When you work with the grain rather than across it, start with the chords. These are the top and bottom horizontal members that run the full length of the bridge. The top chord was in compression, being squeezed horizontally as the load pushed down. The bottom chord was in tension, being stretched horizontally as the bridge tried to flatten out under load. The bottom chord was typically built from multiple layers of heavy timber, sometimes 4 or 5 pieces of white pine, each 4 inches thick by 12 inches wide, laminated together and bolted with iron. This lamination was critical. A single large timber, no matter how carefully selected, will always have a hidden defect, a knot, a crack along the grain, a slight internal twist from uneven drying. Multiple laminated timbers averaged out those defects. If one layer had a weak spot, the others carried through. The diagonal members ran from the top chord to the bottom chord at angles typically around 45 to 60 degrees. These members were in compression, and they were almost always solid, heavy timber. White oak was favored because of its crushing strength, its ability to resist being squeezed without failure. Each diagonal timber was carefully fitted at both ends into cast iron bearing blocks bolted to the chords. A diagonal timber that fit loosely at its bearing point would rock slightly under each passing train, gradually crushing and loosening the wood fibers at the contact surface. Builders learned to fit these connections as precisely as possible, sometimes using thin iron shims to take up any remaining slack. Then came the Howe innovation, the vertical iron rods, threaded at both ends, running from the bottom chord up through the top chord and bearing against cast iron washers on the outside face. Tighten the turnbuckle nuts at the top, and the rod went into tension. It pulled the bottom chord upward and the top chord downward, pre-stressing the entire structure before a single train arrived. The iron rods were doing work constantly, holding the wooden members in close contact, preventing the slight rocking and play that led to fatigue damage. The bridge was, in a sense, always alert. Surrounding all of this was the covering, the famous covered bridge roof and siding. People today think covered bridges are romantic. They are not primarily romantic. They are practical to a degree that borders on desperation. Exposed wood in outdoor conditions rots. A white pine bridge exposed to rain, snow, sun, and temperature cycles will begin to fail in 10 to 15 years. The joint connections where iron meets wood are especially vulnerable because water migrates into the joint and accelerates decay precisely where the load transfer is most critical. Cover the bridge, and the wood lasts 60, 70, sometimes 100 years. The roof and siding kept direct rain off the structure. More importantly, they maintained a relatively stable temperature and humidity inside. The wood dried slowly and evenly in summer, absorbed moisture slowly in winter. The extreme swelling and shrinking that destroys unprotected wood joints was reduced dramatically. The covering added weight, it added wind resistance, it added fire risk, but it extended the service life of the bridge from 15 years to 60. That was the calculation. And the builders made it, rationally, every time. His name was almost certainly never recorded. He was a bridge carpenter, probably in his 20s, probably from one of the mill towns of New England or Pennsylvania. He would have known how to fell a tree, how to square a timber with a broadaxe, how to use a draw knife, a mortise chisel, a wooden mallet. He would have worked from early April to late November, when the rivers were low enough and the ground solid enough to set falsework in the streambed. The falsework, temporary wooden scaffolding erected in the water to support the bridge during construction, was the most dangerous part of the job. You built it first, sinking heavy timber bents into the riverbed with a pile driver. A heavy iron weight dropped repeatedly from a wooden frame. The men who worked the pile driver stood on a plank platform suspended over the water, pulling on ropes in rhythm, chanting sometimes, to coordinate the lift and drop. If a plank gave way, if a rope broke, you went into the river. In early spring, that river was cold enough to kill you in minutes. Once the falsework was in, you began assembling the truss members from the inside out, bottom cord first, laid across the falsework bents. Then the iron rods, threaded through pre-drilled holes. Then the diagonals, each one lifted by a system of block and tackle, guided into its bearing blocks by men working from wooden staging hung on the outside of the structure. A heavy diagonal timber, 30 feet long, 12 inches square, weighed close to 1,000 pounds. If it slipped from the rigging, it did not slip gently. Falls were the leading cause of death. Falls from staging, falls through partially completed decking, falls from the top cord while fitting a bearing block. The work was done at height, on narrow surfaces, often in wet or windy conditions, always with heavy materials moving around you. There was no safety net, there was no hard hat, there was no requirement that an injury be reported to anyone above the foreman level, and the foreman's primary interest was in keeping the schedule. Crush injuries were common. A man's hand caught between a timber and an iron-bearing block as the block was driven home. A foot trapped when a falsework bent shifted under unexpected water pressure. These injuries did not typically kill you immediately. They killed you slowly, through infection, through the loss of the ability to work, through poverty. The bridge carpenters were paid by the day, typically between $1 and $1.50 in the 1850s and 1860s. A good carpenter might work 6 months of the year on bridge work and spend the other 6 months taking whatever mill or carpentry work was available. There was no pension. There was no workers' compensation in any modern sense. There was only the next job. Some men made a career of it. They developed a specialty in Howe truss assembly, or in timber selection, or in the particular skill of driving iron rods to exact tension without splitting the timber around the bearing block. These men were worth more than the general carpenter, and they knew it. They moved from railroad contract to railroad contract, following the construction frontier west. When a bridge failed, and they did fail, the human cost was immediate and visible in a way that slow decay was not. The Ashtabula Bridge disaster of December 1876 is the most famous example. A Lake Shore and Michigan Southern Railway train crossed the Ashtabula Creek Bridge in northeastern Ohio on a winter evening. The bridge collapsed. 11 wooden passenger cars fell 60 feet into the frozen creek below. The fire from the oil-burning heating stoves spread through the wreckage within minutes. 92 people died. 19 more were injured. The chief engineer, Charles Collins, died of a self-inflicted gunshot wound days after testifying before the investigation. The disaster did not stop the wooden bridges. They were too deeply embedded in the railroad economy to be abandoned overnight. But it hardened a conversation that had already been ongoing for a decade. How long could wood hold? To build the wooden bridges of the railroad age, you needed timber. Enormous quantities of timber. A single Howe truss railroad bridge, spanning 200 feet across a major river, might consume 50,000 board feet of structural timber, white pine for the chords and lighter members, white oak for the compression diagonals, hemlock for the decking and siding. Now multiply that single bridge by the thousands of railroad crossings built between 1830 and 1890. Add the constant need for replacement, bridges that rotted out, bridges damaged by flood, bridges weakened by years of traffic. A major railroad line rebuilt its timber bridges on roughly a 30-year cycle, which meant that a line built in 1850 would be rebuilding its original bridges in 1880, even as it was still building new ones further west. The white pine forests of Maine and Michigan, once so dense that travelers reported the shade so deep that underbrush barely grew, gone in the span of decades to lumber camps that operated 12 months a year. Pennsylvania's hemlock forests stripped bare. Ohio's oak forests cleared ridge by ridge. The men who worked those timber camps lived lives as hard as the bridge carpenters themselves, and in some ways harder. Camp life in the winter logging season meant sleeping in a low timber bunkhouse, miles from the nearest town. Men slept on straw ticking in double rows, close enough together for shared body heat. The smell was what every memoir of the logging era mentions first: wet wool, wood smoke, sweat, pine pitch, and the particular sharp smell of men living without baths for weeks at a time. Felling a large white pine, a tree that might be 150 feet tall and 6 feet across at the base, required reading the lean of the tree, the set of the wind, the slope of the ground. Miscalculate, and the tree kicked back on its stump, a phenomenon loggers called a barber chair, sending several tons of wood in an unpredictable direction at terrifying speed. The men who drove logs down the rivers in spring stood in freezing water for hours, using pike poles to free jams that could involve thousands of logs, with the constant risk that the jam would break suddenly and release a wall of timber moving at the speed of the current. And what did all of this produce? It produced a railroad network that by 1880 covered over 115,000 miles of track across the United States. It produced a national economy knit together for the first time, wheat from the Great Plains reaching New York in days rather than weeks. The acceleration of industrial capitalism itself. The wooden bridges were the hidden infrastructure of that transformation. Nobody celebrated them. Nobody named them the way they named the great iron bridges, the Niagara Gorge Bridge, the Eads Bridge at St. Louis. The wooden bridges were invisible in their ubiquity, essential in their ordinariness, and terrifying in their silence about the cost. The wooden railroad bridge did not die suddenly. It died the way most technologies die, incrementally, then all at once, pushed out by something that did the job better and could not be argued with. Iron offered things wood could not. Iron did not rot. Iron did not burn. Every covered wooden bridge was, in a sense, a box full of kindling waiting for a single ember to land in the right place. Railroads employed bridge watchmen whose sole job was to walk the bridge after every train, looking for smoldering spots on the deck and siding. It was a job that required constant vigilance and offered no margin for error. Iron offered something that wood never could: consistency. And in the world of bridge building, consistency was not merely a convenience. It was the difference between a structure that stood and one that did not. A white pine timber might be excellent, cut from the right tree, in the right season, from the right part of the forest, dried slowly over the right number of months. It could be a remarkable piece of material, straight-grained, dense, resinous, strong in ways that surprised those who underestimated wood. It could carry loads that seemed impossible for something that had once been alive, that had once bent in the wind and drunk rain from the sky. A good white pine timber was a small miracle of natural engineering, centuries of slow growth compressed into fiber and grain and resin. But it might also be full of hidden defects. This was the terrible uncertainty at the heart of working with timber, the uncertainty that no amount of experience could entirely eliminate. A ring shake, a separation that formed between the annual growth rings, invisible from the outside, lurking in the interior of an otherwise perfect-looking log, could halve the carrying capacity of a member without announcing itself in any way that the eye could detect. An interior crack, formed during the drying process when the outer wood shrank faster than the inner wood and the tension between them exceeded the strength of the fiber, might run for 3 feet through the heart of a timber and never show itself on the surface. Compression wood, the denser, harder, more brittle wood that a tree produces on its downhill side when it grows on a slope, fighting gravity for decades, its cells deformed by the constant effort of staying upright, looked nearly identical to normal wood and behaved very differently under load. There was no reliable way to detect these defects from the outside. You trusted your timber by eye and by experience, and eye and experience were formidable tools when they had been developed over years of handling thousands of timbers. The men who selected bridge timber for the great railroad projects of the mid-19th century were not guessing exactly. They had developed intuitions so refined that they amounted almost to a sixth sense, a way of looking at a log that processed dozens of subtle visual cues simultaneously and produced a judgment that was right far more often than it was wrong. But sometimes the eye missed something. And when the eye missed something in a bridge timber, the consequences were not like missing something in a piece of furniture or a floor joist in a house. The consequences were felt at the worst possible moment. At the moment when the heaviest load the bridge would ever carry was moving across it at the highest speed it would ever travel. The eye missed something, and the timber failed, and the bridge went into the river, and the train went into the river with it. This is why iron was coming. Not because iron was beautiful, or because iron was easy to work with, or because iron was cheap. In the beginning, iron was none of these things. It was expensive, it required specialized skills to fabricate, and it had failure modes of its own that were poorly understood in the early decades of its use. But iron was consistent. You could test a sample of iron in a laboratory, subject it to known loads, measure how much it deformed and at what point it broke, and then carry those numbers to your drawing board with confidence that the iron you would receive at the job site would behave the same way as the sample you had tested. The number you wrote on your drawing would match the material that arrived. There were no hidden ring shakes in iron. There was no compression wood. But before iron came to replace them, the wooden bridges stood, and standing required constant, unrelenting labor. A maintenance crew assigned to a section of wooden railroad bridges might spend their entire working lives cycling through the same structures, year after year, season after season, in a rotation that never ended because the deterioration never ended. Wood is a biological material, and biological materials return to the earth. They do not hold still, they do not accept the load placed upon them, and then remain unchanged, the way a steel member will remain essentially unchanged under its design load for decades. Wood moves. It swells when it is wet and shrinks when it is dry, and the swelling and shrinking opens cracks and loosens joints and works bolts back and forth until the wood around them has compressed and the connection is loose. It is attacked by fungi that find the moisture in wet wood and begin the slow process of breaking down the cell walls. It is attacked by insects that find the resins and sugars in certain species particularly nourishing. It is attacked by the repeated loading of the trains that pass over it, each pass flexing the members slightly, each flexure a tiny fatigue event, 10,000 fatigue events accumulating into something that the eye finally notices as a change in the way the timber responds to the tap of a mallet. The maintenance crew knew what they were looking for. They might replace individual timber members as they showed deterioration, pulling out a deck plank that had gone soft, cutting out a web member whose end grain had darkened with the telltale stain of fungal growth, swapping in a new cord segment where the checking had gone too deep. They tightened the iron rods that Howe had incorporated into his truss design, the vertical members in tension that ran from cord to cord and whose nuts could be backed off to true up a bridge that had settled unevenly. They recalked the roof and siding of covered bridges, running oakum and tar into the gaps that had opened between boards over the previous year's cycles of wet and dry. They jacked up sections of decking that had settled where a foundation had shifted, shimming and blocking until the deck ran true again and the trains would not feel the bump. The labor was skilled. It was not the unskilled labor of men who had been handed tools and pointed at a structure. It was the practiced work of men who understood timber, who knew how wood failed and could read the signs of impending failure before the failure arrived, who could look at a bridge after a winter and tell you, within a few hours of inspection, what needed to be done and in what order. The schedule was relentless because the bridges did not pause in their deterioration to wait for the maintenance crew to arrive. The cost was ongoing, year after year, with no end in sight for as long as the bridge stood. Iron bridges, once built, required far less. They needed to be painted regularly and thoroughly because the enemy of iron was not fungi or insects but rust, and rust could be held at bay with paint in a way that rot could never quite be held at bay in wood. But painting, even frequent painting, was far less labor than the continuous cycle of inspection and replacement that wooden bridges demanded. The crew could move through an iron bridge in a fraction of the time they spent on an equivalent wooden structure. The upfront cost of the iron bridge was higher, often significantly higher, because iron had to be fabricated in a foundry or rolling mill and shipped to the site, while timber could often be cut from trees that grew within sight of the crossing. But the lifetime cost was lower. For a railroad carrying heavy freight across the same bridges day after day, year after year, the math was straightforward. The ledger told the story clearly, and the ledger was the language the railroad accountants spoke. Then the locomotives got heavier, and the math changed again, and this time it changed against wood in a way that no amount of maintenance could correct. The early American locomotive was, by the standards of what came later, a relatively modest machine, 20 tons, perhaps 30, enough to feel enormous to anyone standing beside it on a station platform, enough to shake the ground when it passed and fill the air with steam and noise and the particular sulphurous smell of coal combustion, but not, in the language of structural engineering, an extraordinary load. The bridges built for these machines were sized accordingly. They were sized by men who were working partly from calculation and partly from experience, who had developed rule-of-thumb proportions that produced structures with margins of safety sufficient for the loads they would actually carry. These bridges stood, and the trains ran over them, and the margins held. But the railroad was a business, and a business expands or it dies. The economics of railroading demanded ever larger locomotives because a larger locomotive could pull a longer train, and a longer train meant more freight, and more freight meant more revenue, and more revenue meant survival in a competitive industry that punished inefficiency without mercy. Every year brought locomotives that were heavier, more powerful, built with better metallurgy and more sophisticated engineering, capable of generating tractive forces that would have seemed fantastic to the men who had built the first American railroads. By 1870, 60 tons was common on major main lines. By the 1880s, 70 and 80 tons were unremarkable. By the 1890s, locomotives exceeding 100 tons were operating regularly on the most heavily traveled freight corridors, pulling trains of a length and weight that made the early railroad look like a toy. A wooden Howe truss bridge, adequate for a 60-ton engine in 1860, was not adequate for a 100-ton engine in 1890. The forces it was asked to carry were not the forces it had been designed to carry. The members that had been sized with a comfortable margin of safety against the 1860 locomotive were now being stressed into ranges that the designers had never anticipated. Wood, under loads that approach and then exceed its design limits, does not fail in the neat, predictable way that iron or steel fails. It does not give you a warning deflection and then a clean fracture. It crushes at the connections, splits along the grain, fails first in one place, and then, as the load redistributes to the remaining members, and those members are now carrying more than they were designed for, fails in another place, and then another. The failure, when it comes quickly. The railroad's choices were narrow, and none of them was attractive. They could limit the loads, prohibit the heavy locomotives from crossing the older wooden bridges, maintain a different set of routes for light and heavy traffic. This was commercially unacceptable. The railroad had been built on the premise that it could carry what commerce required, and commerce required the heaviest locomotives on every line. They could strengthen the wooden bridges, add new timber members, reinforce the connections, try to adapt a structure designed for one world to serve in a different, heavier world. Sometimes this worked, after a fashion, for a limited time. But the fundamental geometry of the original design could rarely accommodate the changes required, and the cost of strengthening was often close to the cost of replacement. Strengthening was often structurally impractical, and what was structurally impractical was also economically irrational. Replacement won. By 1900, major railroad lines had replaced the majority of their wooden truss bridges with iron and steel. It happened in the quiet, methodical way that large infrastructure changes happen, not all at once, not with ceremony, but bridge by bridge, year by year, on a schedule driven by condition and economics and the weight of the locomotives that needed to cross. The last wooden railroad bridges on active main lines were gone by the early 20th century. Some had survived longer than anyone had expected when they were built, had been maintained so carefully, had been rebuilt so many times from the foundation up, that by the end they shared perhaps only their original geometry with the structures that had first been erected decades before. Others had deteriorated more quickly, had been deferred and patched and compromised until they were operating on borrowed time, and had been replaced with a relief that the maintenance crews made no effort to conceal. Most were demolished, taken apart by the same kind of crews that had built them, the timber sold for lumber if it was sound enough, burned if it was not, the iron hardware collected and sold for scrap. A few burned in the unpredictable way that wooden structures near railroad tracks have always burned. A floating ember from a passing locomotive finding its way to a dry timber on a dry day, the fire catching and running through the structure before anyone could respond. Several were swept away by floods when they were no longer maintained, when the maintenance crews that had kept them alive through decades of service had been reassigned to newer structures, and the old bridges had been left to find their own accommodation with the rivers they crossed. The rivers, as rivers do, eventually settled the question. The men who built them are almost entirely nameless. They built structures that carried millions of tons of freight and hundreds of thousands of passengers across rivers and gorges and valleys all across the American continent. And they did this work without leaving behind, in most cases, any record more permanent than the structures themselves. The structures are gone, the men are gone. What remains is the geography. The places where the bridges were, the riverbanks that were worn smooth by the feet of the construction crews, the remnants of stone abutments that still emerge from the water at low summer levels on rivers that haven't been looked at carefully in years. The bridges themselves are almost entirely gone. Stand on the bank of almost any major American river today, and you are standing near where a wooden bridge once crossed. The ground under your feet may hold the shadow of a foundation. The river you are looking at flows through a space that was once spanned by timber and iron rod and the labor of men whose names are nowhere recorded. The concrete and steel structure above you, whatever bridge carries the road or the railroad across the river today, descended from the thinking that the wooden bridge pioneers forced into existence, not directly. Nobody today is building Howe trusses. The specific details of mid-19th century timber bridge construction have no application to a modern pre-stressed concrete box girder or a cable-stayed suspension span. The materials are different, the tools are different, the analytical methods are incomparably more sophisticated. But the habits of mind carried forward, the habit of thinking about load paths, of tracing mentally the journey that a force takes from where it enters the structure to where it is finally absorbed by the earth, was not invented by the wooden bridge builders, but it was drilled into practice by them under conditions that made the lesson impossible to ignore. If you misunderstood the load path, the bridge fell down. The feedback was direct and it was final. The habit of designing for redundancy, of building so that no single failure anywhere in the system causes total collapse, was learned the same way, through experience and through the analysis of failures. A well-designed truss has this quality built into its geometry. Every member participates in carrying the load, but no member is so critical that its sudden failure brings everything else down instantly. There is redistribution, there is warning, the structure protests before it fails. Squire Whipple, the American engineer who published the first scientific analysis of truss bridge forces in 1847, proved mathematically what the bridge builders already knew from practice, that a well-designed truss distributes load so efficiently that no individual member ever approaches its failure point under normal service. The safety margin was built into the geometry, size to what is needed, not to what seems impressive. That principle is still the foundational discipline of structural engineering today. The wooden bridge builders learned it first, and they learned it in the most direct way possible. If you used more wood than you needed, the bridge cost too much, and the railroad hired someone else. If you used less, the bridge fell down. The margin was narrow, and generation after generation of bridge builders found it, and held it, and passed it forward in the form of habits and rules of thumb and the intuitions that experienced engineers develop and cannot entirely explain. What they could not pass forward was the forests that built them. The white pine forests of the Great Lakes states were essentially gone by 1900. This is a fact that can be stated in a single sentence and that requires, to be truly understood, a much longer meditation on what those forests were and what their disappearance meant. A forest that had taken centuries to grow, that had been building itself since before European contact, growing its great straight trunks skyward in the particular way of trees that have the space and light and time to reach their full expression, was consumed in 50 years. The mills followed the timber north and west until there was no more timber to follow, and then they stopped, and the cut-over land lay exposed and barren, and the rivers that had carried log drives of staggering size ran clear and empty. The skills that built the bridges also largely vanished. The craft of timber framing, of reading a log, selecting it for its specific structural properties, cutting complex joinery without metal fasteners, fitting large timbers together so that they functioned as a unified structural whole, nearly disappeared in America. The intuitive knowledge of how a large timber behaves in service, how it moves through the seasons, how it carries load along the grain versus across it, how to read the signs of fatigue and distress in a structure made of wood, this knowledge had to be partially reconstructed from scratch by engineers in the late 20th century who became interested in mass timber construction. That reconstruction is ongoing. The current interest in tall timber buildings, in cross-laminated timber, in glulam frames, in structures that reach heights that would have seemed impossible to the men who built the railroad bridges, is, in a sense, a return. An acknowledgement that the material the wooden bridge builders used was not primitive. It was appropriate, it was local, it was renewable, and under the right conditions, shaped by the right hands and the right understanding, it was strong enough. Strong enough to hold 200 tons of steel locomotive pounding across a 100-foot span at 40 miles per hour, morning and night, year after year, in the rain and the cold and the summer heat, until something better came along. That is what the wooden bridges did. They did it without recognition, without ceremony, in the ordinary course of a business that demanded reliability and cared nothing for sentiment. They did it in the snow and the spring floods and the long dry summers, when the timbers shrank and the joints loosened and the maintenance crews tightened everything back down and moved on to the next bridge. They did it for 50 years, and then they were replaced, and the replacement was right and necessary and economically rational, and the bridges accepted their replacement with the indifference of objects, which is to say without any acceptance at all. And if the men who built them had any memorial at all, any monument more lasting than the rivers they crossed and the forests they consumed, it is this: the trains ran, the continent connected, the country that emerged from the railroad age was built on a foundation that was, more than anyone now remembers, made of wood.